Good afternoon, Directors, Chair. For the record, I'm Tony Morgan, Deputy General Manager for Groundwater and Water Resources at United Water, and I appreciate the opportunity to talk to you today. We're going to chat about the South Oxnard Plain Brackish Water Treatment Feasibility Study that United has just completed and give you an update on where we are with that project and just introduce you to the concepts that go around with that project. Let's see if we can go. Excellent. Okay, background on the project we're going to talk about today, some issues of water quality and why we are considering this particular project. We'll talk about the processes and the design of this treatment facility, a little bit on cost and some conclusions at the end. So why are we talking about this project? Let's give a thumbnail sketch of what the idea is. We need to start with an overview of the project and think of this project as a new water source. The concept was to explore the idea of a brackish water treatment facility as a new water resource and to sort of change the dogma, change the thinking. In the past, we've operated a lot of the time under the impression that having seawater intrusion in our aquifers is a bad thing. And so our management decisions were based in part on how are we going to manage that. Are we going to push it back? Are we going to control it, keep it where it is? And that's such a rationale. What we're offering today here is the other side of the coin. Let's look at this situation where the intruded aquifers can be an asset, and then how would we take advantage of that situation and turn it into an asset. So what's the concept? The concept is we're going to go down to the area near the coast where we have the intruded aquifers. So you can see that area there. Okay? We're going to extract the water, treat it, and deliver that water into the PTP and the PV systems. That gives us access to a large number of folks who can make good use, make beneficial use of that groundwater there. So the extraction well field is your source of water. In the future, it's a barrier to seawater intrusion. We'll talk more about that in a moment. Okay. We have a disposal mechanism. The SMP pipeline is nearby. The treatment technology is there. It's relatively simple to make that water into a quality that's acceptable for agricultural use. And it's a pretty flexible operation. If we don't need the water, we don't have to run the plant. So let's step through that in a little more detail. This is the concept, and so you have an idea of where we're going now. So let's take a look at what we're dealing with seawater intrusion with right now. This is the classic presentation that you've seen from United and others on how seawater intrusion has been portrayed on the South Oxnard Plain. And so the Hueneme Submarine Canyon is a source for this lobe of impaired water. The Mugu Submarine Canyon is the source for this lobe of impaired water. And so we map that out based on these red wells out here, who are monitoring wells, and some of the blue wells out here, which are water supply wells. So we're using that water quality to map out what we think the areal extent of it is. We understand that during periods of low water levels, which we have right now, okay, we see, and let's just talk about this lobe right here, for example, seawater intrusion comes in and begins to move inward. As it moves inward, we come out of a drought period, water levels come back up, and instead of that impaired water retreating back offshore, what happens is it's swept down the coast. Okay, so we don't push it back offshore all the way. Some of it moves down the coast. Okay, and that's a function of the water levels and the gradients that we establish by recharging the forebay and other areas. So as we push that down the coast, we leave some of it out here on the South Oxnard Plain. And so I want you to pay particular attention to this little area right in here. So there's Hueneme Road, just to give you an orientation. There's Edison Road. There's Arnold and Casper. So remember that area because we're going to come back and talk about that again in a few moments. In 2010, United did a surface geophysical study to try to map out in a little more detail where we think the saline water is. Okay? And we come up with a depiction like this. There are several maps of this sort that your staff and yourselves have seen in various documents from United and from staff here. Basically, the dark blue is the saline waters. The sort of turquoise-ish light blue is the brackish water, and the gray is the slightly brackish water scenarios. What do we surmise from this? The leading edge of the seawater intrusion is not a front. It's not a wave. Okay? It's got a very ragged front edge to it, okay, which makes it a little more difficult when you're trying to design a remediation system or a mitigation system with an ejection barrier well field, for example. So as we're looking through these kinds of data, we realize that not only does it vary by depth and by place and by time. Okay? So if we look at a single well as an example right here, okay, and we look at the various depths from which we have water samples, we can see what the chloride concentrations do over time. And let's just use this first one as an example. The blue bar represents the maximum chloride value in that water, in that well in 1990. Red represents the maximum value in 2009. The sort of yellowish color there represents the maximum seen over that roughly 19-year window. So when someone asks me, how far inland has the seawater intrusion moved, I got to know where on the ground, at what depth, and when did you ask that question to be referred to? Because the information is different as we go. So this is not just a standalone situation. Here's another well, very similar kind of scenario. So it's a complicated situation, and we think that the proposed brackish water treatment plant offers us a scenario to get around some of this complexity and deal with it from a groundwater management perspective in the future. So let's talk about the treatment feasibility study. What did we do? United commissioned Carollo engineers to prepare a feasibility study. Major questions: is it technically feasible to take that brackish water and treat it? Okay. And would that desalter plant give us a long-term reliable supply of water? We looked at whether or not there was raw water available. Is there a brine disposal option? And would we have a place for that treated water to go? And so we'll talk about that in a moment. When you design these kinds of treatment facilities, the rule is you tell me what you're starting with, you tell me what you want to end with, and then we'll decide what we do in between the two endpoints to get there. What treatment technology is going to work best. And so we started out by looking at those red dots you saw out there on the earlier map. Those are our monitoring wells. We gave that water quality to the consultants. They came up with a composite raw water out there. And then we wanted a series of buffers on that, a security. So that number was increased by 50%. And so we ended up with what we thought was our maximum worst case water quality out there. The guise is here, we're going to design the treatment facility for a TDS ranging, let's just call it 6,000 to 10,000 milligrams per liter. That's the target operational scheme for the plant. Okay, that was the raw water. Here's the product water. Here's the treated water. So we talked to a few of the agricultural folks and said, what would you like to have? And so this is sort of the water quality that we came up with. This is pretty decent quality water. Is it as good as coming out of the AWPF? No, it's not. TDS is not as low. A few of the other parameters aren't quite as low. But it's pretty good quality water. And it meets potable standards for a lot of things. Not quite all, but most of it. So now we have a raw water. We have a product water, what we're going to get to. So how did we come up with a technology? 3 of them are looked at: reverse osmosis, electrodialysis, and distillation. Decision was not practical. Certainly not competitive, cost-wise, at the concentrations we're talking about dealing with. So we're talking about a system that's reverse osmosis-based. We're pretty far along in the feasibility study with the process design for this plant. We've got the 3 main stages, the pre-treatment, the RO system, and the post-treatment, all lined out. So we've gotten pretty far along with it, so we feel confident when we say we think this technology is feasible, that we've taken into consideration several of the major variables. We asked the engineers to do this kind of design for 2 different treatment capacities. One is a 10,000 acre foot per year plant. The second is a 20,000 acre foot per year plant. And so just to give you a little bit of a visual, that's kind of what the 20,000 acre foot per year facility might look like. There's a large storage tank on there for some more or less instantaneous capacity. That's about a 4 million gallon tank that would hold approximately 5 hours worth of production at a 20,000 acre foot per year plant. Okay? So where would this plant and the associated well field that we mentioned earlier might be located? Okay? For the feasibility study, you have to give the engineers a spot on the ground. You have to say, we think the plant might be here, we think the well might be over there, and they work out the piping system accordingly. So for the purposes of the feasibility study, and for nothing else, we haven't selected any locations, but for the feasibility study, we had a system here with a well field, proposed desalter facility there, and just to orient you, this is Hueneme Road. There's East Pleasant Valley Road. There's Edison. It gives you an idea of where you are. There you can see the airfield at Mugu. Hueneme is off the edge of the slide here. Green line is the SMP, the salinity management pipeline. That would be our brine disposal facility for this project. The concept is with the product water, that which we've made out of the treatment plant, that would be delivered up to the PTP system, and the pipeline extended on out and connected to the Pleasant Valley County water system there. That gives us access to a lot of users out on the coastal plain area. The well field is 12 wells as proposed. The desalter facility is listed here. Okay, that's about a 20-acre parcel that's been identified of MWD as a future site of a desal facility. There's a lot of interest in that facility with respect to the Ormond Beach restoration efforts and that kind of thing. So that facility doesn't have to be there. It can be anywhere out here. It doesn't. That's really not a material factor in this discussion. So one of the beauties that we think we've built into this system is that not only are we delivering water out here to satisfy some of the active irrigation demand, if we can tie into those systems and the wells are appropriate along those systems, those wells can be used as injection points during periods when we have low demand, diurnal periods. At night we don't need irrigation water, but we need it during the day. So at night the water can be used to recharge the aquifers directly. In worst case scenario, a pipeline could be built and the plant's product water could be delivered to the spreading grounds in the forebay that United has and used to replenish the aquifers there. But for this project, we're looking at two main distribution systems into the PTP and into the PV. And we'll talk more about that in just a moment. One option that's come up relatively recent, and let's zoom in just a little bit on the image here, is the city of Oxnard is looking at acquiring some vacant land near the AWPF facility for a park and some other things, and they have expressed at least an early interest that if the brackish water treatment plant wanted to be located there, they think a 3 or 4 acre parcel, which is about what that plant size would be appropriate to there. So we have some options as to where we might locate. Notice that everything we have drawn here is just inside the Coastal Commission boundary. That's the red line on this one. So we're inside that boundary.
What boundary is that again?
Coastal.
That's the Coastal Commission boundary. Okay. So now we're talked a little bit about the well field here. Why here? Well, one of the easiest things is construction logistics. Constructing a well field, pipeline and wells in an agricultural setting is much easier than doing it in an urban setting. There's less headaches and grief and construction costs associated with that. But there's a more technical issue that goes along with it. So if you remember back earlier, I gave you the map showing the extent of the seawater intrusion. If we overlay that with the proposed wellfield location, we'll see that we're right in a decent spot right here to intercept both the seawater intrusion from this direction and the seawater intrusion coming from the Mugu area as well. So we've got a situation where we're right in an area where we have a mix of higher TDS wells, lower TDS waters, and when we blend those two, we think we can remain within our 6,000 to 10,000 TDS operational scheme. Okay. The slide you've all been waiting for is the money slide, right? So what are we looking at for this project? Two sizes, 10,000 acre foot year and 20,000 acre foot per year. Capital costs running from, let's just call it $85 million to 148 million, depending on the size of the facility you wish to construct. Okay. Recovery costs, that I mean capital O&M, annual O&M and capital recovery rather, you're looking at something on, let's call it $1,000 to maybe $1,200 an acre foot as a reasonable number for this kind of technology. So as we queried the consultants, the engineers on this project, give us the answers we're looking for. Do we have raw water available? The answer was yes. Is it technically feasible? They said definitely yes. This is not rocket science that you're asking us to do. This is standard off-the-shelf technology. Do we have a brine disposal option? Yes, we do. The S&P pipeline is in place, and much to the credit of Callegas, that facility is now available for us to use. Brine disposal is usually the stumbling block for these kinds of projects. There's no place to put the brine that's economical. We now have a venue for that. Are there places to send the treated water? Yes, there are. Okay. Are the costs viable for a long-term water supply? We think they are. Water costs are going to continue to rise. This $1,000 to $1,200 number is right there in the same ballpark as others. Now, with any project, there's pros and cons. Let's talk a little bit about the cons associated with it. We may induce seawater intrusion towards the well field. I don't think there's any may about it. We will. We're talking about pumping, let's say on the 20,000 acre foot facility, we're going to pump 28,000 acre feet of impaired water to generate 20,000 acre foot of treated water. Okay. We are going to induce seawater intrusion, but we don't really care so much because it's going towards our well field. We're going to control it. It goes towards the well field where we can extract and treat that water and use it as a source for our facility. Might the TDS increase in the future as we pull more seawater towards our plant? Possibly yes. Possibly yes. And we'll have to do some modeling to determine how fast and to what degree that occurs. But remember, at the same time, as we're inducing seawater intrusion towards the well field, we're also inducing cleaner water to come from inland areas towards the well field also. So there's going to be some sort of balancing effect that occurs with that. So we think that's a doable scenario where we can keep the TDS within the range we need for operation of the facility. We may impact water levels and water quality for some upper system wells near the well field. That's correct. We probably will. The wells that are out in that general area are irrigation wells. So if that's the scenario, the mitigation is relatively simple. They tie onto the product distribution line to replace their water with the treated product water from out there. There are some pros that go along with that also. It has a water supply benefit. It's a reliable new source of water. It's sustainable. We've got the ocean there as our source water, so we're not going to run out of that in any foreseeable scenario. There's some water quality benefits. Early in the project, during the extraction phase, we're going to be doing a bit of aquifer rehabilitation. We're going to be pulling some of that brackish water out and making the water quality better. Later in the project phase, it's going to shift into more of the extraction barrier scenario, where we're going to induce flow towards the well field, induce the flow towards where we want it to go. So if there's a drought in the future, that's fine. We've already got the hydraulic system set up to capture that and bring it towards the well field. Okay. Groundwater management. There's in lieu recharge benefits here. We're going to deliver water to PTP and PV systems so that there could be less pumping out there. There's also direct recharge in that we can have the wells on the PTP system, for example, act as injection points. So when we have excess water during diurnal periods, nighttime, rainy weeks where we don't really need the irrigation water, we have the ability to put that water back in the ground directly. And we've got a pretty flexible operation. Unlike a wastewater treatment plant that has to run pretty much 24/7 because it's got a steady stream of product coming to it, in this case, if there came some scenario down the road and we didn't need water for any reason for 2 weeks, shut the plant down. It's not a big deal. The technology exists to shut down and restart a plant like this, and it's relatively straightforward. Okay, where are we at? Next steps. We've collected some additional water quality analyses out there in the proposed well field area. We want to look at things like pesticides, chlorinated solvents, metals, things that we don't normally do in our water quality analyses to make sure there are no hidden speed bumps along the way as we move forward. We're doing some grant research. We have a consultant on board right now that's trying to identify grant opportunities. There are a lot of money floating out there in the state and federal programs, and we think this project will be viewed very favorably by those folks with grant money to distribute. And we're in the middle of the stakeholder outreach. I've got several meetings with various entities to go through this project, answer questions, and address what's going on there. Coming up shortly, we need to get the real estate for the treatment plant and the well field tied down. Okay, we need to make some decisions as to where we think that treatment plant, if it's over by the AWPF, that's fine. We just need to know so that we can begin to lay out piping and well field designs that are appropriate for that. We'll do some exploratory test holes out in the area of the proposed well field to make sure the water quality is what we think it is there with each depth. Remember, we're only talking about the upper system, so we're talking about, maybe down to 400 feet, something like that below surface. Finally, we need to get a electrical power load study initiated with Southern California Edison, but they can't start that to decide until we decide where we want the plant. Where is that big power demand going to be? And if it's by the AWPF, that's one thing. If it's out towards the agricultural area, that's a totally different thing. And so we need to get that done so we can get ready to start the CEQA process. We know that when we start the CEQA process, one of the speed bumps we're going to encounter is greenhouse gases. Okay? Because RO membranes are power hogs. They're a power-intensive operation. And so one of the ideas that we're talking about is, does this project benefit from having solar power included as a component of it? The one thing United does have is land. Okay? So if a solar field helped us get through the CEQA process and offset some of the demand that we would place on the system, then we'll explore the idea and see if solar power makes sense for us. As far as next steps, there need to be some probable GSA conversations. The project benefits from this effort can be realized if the product water, if the treated water is used to offset demand, offset our existing demand, and isn't used to expand demand out on the coastal plain. So that's something that the GSA needs to consider as they move forward. And if this project moves forward, how would that take place? How is that new water going to be used within the system as we work towards a sustainable pattern? There's a fundamental shift in how groundwater and water is going to be managed in the future in Ventura County. This sort of, we'll call it a strategic inflection point in groundwater management, is going to require water policy folks, such as everyone in this room who are involved in that in one form or another, to think about things that in the past weren't palatable. Things that were too expensive, idea too far out of the box. I think we're moving into a time where we're going to look at things with a little bit different shade in our glasses as we review water sustainability programs. Anyway, this project falls clearly into that realm. I won't take any more of your time today. If there are any questions, I'll be glad to